Hello, today's lecture is a continuation from the previous lecture about the three general patterns of the complex limit equations that requires the fundamental identities and the concepts of utilization of the concepts of the first principles to solve. We covered the two general patterns from our previous lecture, and today, thus, we'll be covering our third, however, last but not least, the third general pattern of the complex limit equations. And although I said that from the previous lecture that the third pattern is generally a little bit more harder than the first two patterns, this may be my prejudice or my bias. It might not be for you. However, even though I said that it was a little difficult, I just want you to say, despite the difficulty of these patterns, the fundamental tools, the fundamental way to solve these questions, the approach to solve these problems never change, are steadfast, are always the same. So therefore, what was the steps to solve these type of complex limit questions? Well, first, I told you to generally, you have to 100% understand the identity of the first principles. That's why I already wrote it over here. You know how many times I've emphasized this before for the last 3 lectures, right? So you have to know what this first principles actually mean. I mean literally everything that this implies. What do you need? What does the limit equation, what should the limit equation satisfy for the instantaneous gradient at x equals a to be existing? Well, the average rate of change between x equals a and x equals x of the function y equals fx, the average rate of change between these two points when x infinitely gets closer to a from both positive and the negative side, the approaching limits of both average rate of changes when x or h approaching 0 from both the positive and the negative side should yield the same results to be defined into f prime a. Okay, and what's the second step then if you 100% understood the concept of the first principles? The second is you have to know, since you've known the features of this identity, now you have to know the visuals. And by that, I mean the literal aesthetics of this formula. Just look at the design of this formula. Look at the coefficient h's on both the denominator and the numerator, and also the h on the below the limit symbol. What does this imply? Well, they have the same order of power, they have the same coefficient. So, since this limit equation shows signifies f prime a, then whatever limit that we have, we're trying to define it as an identity or the formula of the first principles, then we also have to tailor those equations where h on both the denominator and the numerator and also below the limit symbol are exactly same with one another. However, it will be better if we can tailor it into a form where it has the coefficient of 1 and also the order of power of 1 as this formula exactly shows. And to tailor the equation in form of that, well, from the previous lecture, to apply that to our two general patterns, we used the process of substitution to do that, right? But you have to know that even though we're trying to look at the features and the visuals of this formula and we're trying to change the equation that we are given into a form of the first principles, well, even though you do so by using a tool of substitution or whatsoever, you will also have to reinterpret the formula. You will also have to reinterpret the equation that you got, the tailored equation of the first principles as you got, because your tailored equation of the first principle may not actually imply the actual meaning of the instantaneous gradient at x equals a. For example, from our first general pattern, there was a case like, depending on the order of power of h, whether it was an odd number or an even number, when it was an even number, then it couldn't be, although it had the same format as the first principle, because the range of h to the even number power could not be negative, the first principle could not be defined. It could only be interpreted as the instantaneous rate of change where x approaches a only from the positive side. So therefore, you will also have to reinterpret its meaning after you have tailored the equation after you've tailored your given limit equation into a form of the first principle. So, I so much apologize for making this so confusing. So first, understand the steps for solving the questions. First, understand the first principle identity. Second, think of the visuals. Think of the exact visuals what should have that the limit equation should have to be exactly defined into a form of the first principles. Now third, use the process of substitution whatsoever to transform your given equation into a form of the first principle equation. And then fourth, lastly, reinterpret your tailored form of the first principle equation into if you can, to a meaning that it deserves. Well, what I mean by that is, if you tailor your given equation into a form of the first principles, or into a pattern of the first principles, then try to give it a definition whether it is actually f prime a, or it looks like an f prime a, but it cannot be defined as an f prime a, such as the first general pattern that we saw when h had a coefficient of an even number. H had a power of an even number. Okay, so then the final third pattern, I know, sorry for taking too long for the revision, so let's just dig in. So example. Here comes our example. Let's say this is our example. Well, this looks pretty confusing, doesn't it? Well, however, as I've explained before, the principle doesn't change. You see a similar type of format, right? You see a similar type of format here. So, in these type of equations, what did I say? You're always trying to tailor it into the form of a first principle equation. So, what can you see from here? Well, first, I don't need to care about the features it has. This is too complicated already. Let's just look at the visuals first. What does this imply? Well, a f parentheses, and there's both a and h in it. In a single first principle equation, there is one f parentheses with both a and h in it. However, there are two of these in a single equation. What does this imply? Well, if you do a little bit of thinking here, you're always trying to tailor it into the form of the first principle. And for each of the first principle equation, they contain one f parentheses that contain both a and h. However, there are two of f parentheses containing a and h. So therefore, this kind of implies that there should be two equations of the first principle equation, two first principle equation in this single limit equation. Wow. Okay. Then we have to create two first principle equation out of this single equation. And how can we do that? Well, what are we missing here? Let's say, just ignore this. If I say that this wants to be defined as the form of the first principles, then I need to have negative minus fa. I need to have minus fa. Okay, so just write it. Let's just write it. Let's just be selfish here. Let's just artificially create fa to satisfy this and this form. However, what about this? Well, before thinking of this, I first need to cancel this out, right? Because the overall equation must have no external change, right? So, sorry. Since I first did negative fa, to cancel this out, since this did not exist initially, then I will have to add fa to cancel it out properly. Then, if I reevaluate the equation one more time, what happens then? I'll evaluate one more time. I will try to write this all into a form of the first principle. So this becomes fa plus 3h minus fa. So this becomes to sort of a form of the first principles. And there was initially a negative. I will just do parentheses here. F parentheses minus 7h. And then since this is plus fa, however, it has been cut out by the minus here, it will also be negative fa. Oh my god, then something magical happens, doesn't it? Well, because of this negative here, this positive also becomes a negative. So this means that these two are both in a numerator form of the first principles, right? So then what can we do? Well, since now we see with the common factor of a denominator, then we can see two first principle equations, right? We finally see the two first principle equations. Then, without infringing the law of the limits, we can split it out between this and this. And 2h fa plus 3h minus fa, then it becomes minus 2hn over fa minus 7h minus fa. And then a big parentheses to close it. Well, we can split this because we can split these apart as two separate discrete fractions because this is in a limit, so it has nothing to do actually with the limit right now. We're just manipulating the equation inside the limit. So any data manipulation inside the limit can take place because we're doing nothing on change. We're just splitting it up. There's no limit concepts to be interfering right now here because we haven't applied the limit equation yet. However, what do we want to do here? Well, we want to interpret these as an identity of the first principles by tailoring them. Well, we already tailored them into a form of the first principles, but now through this limit, we want to give each of them an interpretation that they deserve. However, let's just say that fa prime a is equal to 5 like the previous one. Okay, so continuing back here, we want to give each of them a separate limit here, right? So that they can each be identified, they can each be classified into an identity of the first principles, right? Well, however, this is the difference here. What makes this equation different from the other general patterns were, they were just given single limit first principle equation. There were no two first principle equation inside a single limit. So therefore, however, since we want to separate these two and give limit identity to each of these two equations so that each of them can be separately be considered as separate first principles, we need to satisfy one big limit concept here. This corresponds to the law of limits. If we want to apply limits on both two equations, both two fractions here, then we must have a really big supposition that each of these limits must exist. Each of these limits must have a value that they are fixed value that they are approaching to. For each of these two separate fractions to have separate limit symbol within them. So therefore, what does this imply? Well, this limit should exist and this limit should exist. Well, we know that if we put limit on both of these equations, then they will be able to be identified into a form of f prime a. However, if f prime a does not exist, then we cannot separate these two into each limit equations because, in the first, this corresponds to the second pattern, right? This corresponds to the second pattern we discussed in the previous lecture. And if in this previous lecture, it did not matter whether the limit existed or not, because no matter it existed or not, we could just represent it into a form of f prime a, like constant times f prime a. However, here, for us to do that, we must separate, we have one more task to do. We have to give limit identity to each of these fractions here. So, we must go into supposition that f prime a must exist for these values to each have a limit identity. That's just the law of limits. So, one more repetition here. I know it can be difficult to understand, but for us to put limit not only entirely, but on separately this fraction and this fraction, so they can individually be recognized into a form of constant times f prime a, this limit separately needs to have a fixed value, needs to exist. Must not diverge into infinity or anything, but must converge into a fixed value. However, what is the supposition for that? Well, what can this limit can be interpreted as? Like the second pattern, can be identified as a form of the first principle, which is constant times f prime a. So therefore, if f prime a does not exist, then basically implicitly saying that this limit does not exist. And since if f prime a does not exist, it means that both of these limit equations will not exist, will not have a fixed value that you're approaching to. So unless there is a supposition that f prime a exists, then there is no way that we can actually solve this equation. We can give limit properties to separate limit properties to both this equation and this equation. So therefore, what I ultimately want to say is, there must be a supposition always to these type of questions that f prime a exists, or f prime a is a constant. And now, since we are given that supposition here, that means we can now separate this limit and this equation into two different limit equations. So this will become limit h approaching 0 2h a plus 3h minus fa, and then minus limit h approaches 0 2h fa minus 7h minus fa. Boom! Now easy peasy. Now easy peasy. What can this be represented as? Well, this corresponds to the second pattern that we learned, right? So we already know that f prime a exists, and this can be represented into a form of f prime a, right? So I said that this equation is equal to, first just write f prime a, however, divide the constant before the f prime a, the constant multiplied by the f prime a is equal to the coefficient of h of the numerator divided by the coefficient of h on the numerator. So it will be 2 over 3. And also, what about here? Minus. This also corresponds to the second pattern, right? So what does this say? So it will become f prime a, and what is the coefficient of the denominator, of the numerator of h? -7, right? No need to be scared because it is negative. You always have to tailor the equation so the denominator and the numerator, they are both same with each other. So this also corresponds to the form of the second pattern. There's no difference because it has negative as in front of the coefficient. It's just the same thing. So considering that it is the same thing, so the coefficient of what will be multiplied by the f prime a will be the coefficient of h on the numerator divided by the coefficient of h on the denominator. So it will be -7 divided by 2. So -7 divided by 2, -7 divided by 2, f prime a. However, since there are two negatives, I can set this as plus. So erasing the parentheses that I don't need, I will be able to write this as this. Plus 7 over 2 f prime a. And what does this ultimately equal to? This is equal to, just add these all up, 10 over 2, which equals 5. So 5 f prime a, which is equals to 5 times 5 equals 25. Congratulations. That was the third pattern that we are going to discuss. However, I also want to describe to you the general pattern to solve these type of questions. The general type to solve these kind of questions. So, I said that these questions can only be solved. These questions can only be solved by using the property of the first principles, only by the supposition that f prime a exists. Because if you want to separate this limit equation into two separate limit fractions equations of the first principles, then this limit and this limit all must exist. And since this can be represented into constant multiplied by f prime a, if f prime a does not exist, then this limit cannot exist. So therefore, f prime a must exist for these limit to exist. So therefore, f prime a must be the supposition for us to separate these two fractions, both give titles, to give the limit characteristics to both these two fractions separately. Okay, however, by looking at the generic equation here, you always don't need to calculate it this heavily like this. There is a formula to do that. Well, let's say limit h approaches 0, and then let's say, since we're trying to find someone related to f prime a, let's use bh here. And let's say f a plus ch minus f a plus dh. So we're trying to calculate this, right? Then what can we get? What kind of answer do we get? Well, by using the same principles here, we can also negative minus fa plus fa to artificially cancel these out so that there's no external change to the entire system equation. However, we can add the properties that we can tailor into a form of the first principles, right? So this will equal to limit h approaches 0, and then bh f a plus ch minus fa, and then minus from here bh a plus dh minus fa, making them both tailored into a form of the first principle. And all we need to do is give limits to both these fractions. However, we need a supposition that f prime a exists for these limits to be both given the identity of the limit equation, right? However, the supposition here, f prime a exists and is a fixed value of 5. So therefore, we can say that this equation can be written once again. I'm sorry if it is a little too small. I still have one more thing to cover here. So that's why I'm making it too small. So bh fa plus ch minus fa minus limit h approaches 0 bh a plus dh minus fa. And what is this equal to? This is equal to, looking at this second generic pattern we discussed in the previous lecture, f prime a, what number is multiplied before? C over b minus f prime a, and then d over b, which is equal to f prime a. However, what is multiplied? b c minus d. So this is the generic pattern for solving this type of equation. However, the most important thing, you must always have a supposition that f prime a must exist to be able to represent this equation into a form of f prime a. If there is no supposition that this exists, if there is no supposition that f prime a exists, then this equation cannot be separated into two separate limit equations. This equation cannot be separated into two separate limit equations, and therefore it is going to have an entirely different value that has nothing related to the first principle. Only because of this supposition we can relate this equation into a form of the first principle. You must always remember that, and that is the key. That is the most important thing that you should take away from from the third generic pattern. And because there are so many things to consider in this pattern, that is why I said that this was a little bit more difficult, the most difficult pattern out of the three patterns that we were going to discuss. Okay, so an easy tip to remember here, let's say f prime a exists, there's a supposition that this value exists, and you were asked to solve a question. But let's say, for example here, 5h here, limit h approaches 0, f a plus 2h minus f a plus 3h. How can we solve this? Well, since there is a supposition that f prime a exists, we just have to follow this general formula. And what is this? Well, first we write f prime a. However, what is the constant that is multiplied by f prime a? C minus d over b. So c, the coefficient of h on the first parentheses of f, so c2 minus d. D is the second f parentheses, the second coefficient of h. So minus 3 over b, which is the coefficient of h on the denominator, 5. So what can this be evaluated as? 2 minus 3 over 5 is negative 1 over 5. So negative 1 over 5 it is. Yeah, negative 1 over 5. This is the answer. So It is really, really easy, right? However, only because of the supposition that this exists. Okay. So what I want to do finally is a brief recap, brief review of the 3 types of pattern that we have learned. However, I just want to first mention, the first principles equation. This equation, no matter what, even if f prime a exists or not, this equation can be always written in this kind of format. Even if f prime a does not exist, we can always write this, that this limit is equal to f prime a. Because this is just an identity. This is just a definition. Even no matter if it exists or not, it is never wrong to say that when at both point x equals a and x equals x of the function y equals fx, as x infinitely approaches a, then the average rate of change between these two ever getting closer and closer points will approach the instantaneous gradient at x equals a of the function y equals fx, also known as the instantaneous gradient, also the differential coefficient of x at x equals a, or also f prime a. So this definition, this identity never changes, right? Can be always written into this kind of format. And by looking at this and by studying this identity, by understanding it, by looking at our second generate pattern here, let's say like BH over A plus CH minus FA. This is just a closing parentheses. This also can be always be written in form of constant multiplied by 3h. In this case, the constant of the numerator divided by the constant of the denominator of both h's. Constant of both h's. So this also can always be written in the form of f constant multiplied by f prime a, can be always written in this format even if f prime a exists or does not exist, because the only thing that differs is multiplying the other constants, right? However, the constants have nothing related to do with the definition of the first principles. So therefore, they can always be removed outside of the system and multiplied afterwards. The inside limit value is calculated. So therefore, since this inside limit value, when the constants are extracted, coincide exactly with this first pattern of the first principle identity, there is always no contradictions. It is always correct to represent this format into constant multiplied by f prime a. And the third, this format here. It's probably too long, but I'll still write it. BH fa plus ch minus fa plus dh. This equation, however, has an exception, right? These one, even though f prime a existed or not, could always be defined with it as a term of something multiplied by f prime a, because it is an identity, right? Because it has no flaw. We're just going by the identity that this equation has. Even though this f prime a did not exist, this limit always existed f prime a. However, this exact value, when we ask about it, will be said does not exist. However, just by representing this in a format was always correct. However, this equation, unlike these above two equations, cannot be represented in the form of f prime a. Why? Because this limit rules restrains it, blocks it from being separated by two separate limit equations unless we have a supposition that f prime a exists, right? So, for this to be represented into a format of c minus d over b f prime a, then we must have a supposition that only when f prime a exists. And, well, if you thought that I forgot to mention, well, actually, what about the first pattern we discussed, right? When h has like an even number power or odd number power. Well, that depends. That depends. When it is an even number power, it can always be defined as f prime a, because when it is an odd number, when h has an odd number power on both denominator and numerator, it can be represented as f prime a because they share the exact same characteristics, right? However, when h has an even number power, then it cannot be defined as f prime a, because it is just a definition of the instantaneous rate of change when x is approaching a only from the positive side, right? So that is not to be considered in the option. And however, these two examples are simple. However, the third one, I really want you guys to really think about it. That is why I said, because we need the law of limits to understand this formation, this transformation here. So that is why I said that the two key factors, understanding of the first principle's identity, shown from these two examples, and the direct comprehension of also the limits in the continuity section, which can be shown from the third section here. So the two factors should be an indispensable tool for you to generally comprehensively understand all these three general topics that we discussed. And however, even though we discussed like these three general topics, these three general patterns here about the complex limit equations, there are still like a lot more complex limit types of equations that I have not discussed of. However, I still want to say that these three general topics, these three general patterns that I've discussed from both last lecture and today's lecture, are the most prevalent types of complex limit equations that will come out or be expected for you to solve, at least in the high school level. Or if there are more ifs, in case of a contingency when other types of complex limit equation comes out, however, there could be a case, right? In that case, I always want to encourage or emphasize you to never be frightened. However, always think that you are going to try, always tailor this equation into a form of the first principles. So let's go over one more time. When you find a question that doesn't belong into a category of these three patterns that we discussed throughout the following two lectures, this and the last lecture, what are you going to do? First, also look at the feature, understand the identity of the first principles. Second, what do you do then? Well, whatever you try to do, always try to tailor the equation, tailor the type of equation that you have into a form of the first principles. Well, try to use a process of substitution or whatever you can to do so. And when you tailor it into a form of the first principle that complies to both the first, the second, or the third pattern, try to give it a mathematical interpretation that it deserves. Whether it can be defined into a form of f prime a multiplied by a constant, or in a different type of interpretation, such as the first case when h has an even number power and cannot be defined as f prime a. Yeah. So no matter what type of harsh conditions, no matter what type of questions that you get, you always have the solution to solve it. Always tailor the equation into a form of the first principle identity and try to solve it based on the interpretations that you have by tailoring the questions that you get into a form of the first principles. It will be a smooth transition, and I want to say just congratulations and thank you for listening to this lecture, despite I said that it was only an optional lecture. I'm pretty sure that whatever contents that we've covered today, although my lecture could have been a little confusing for you guys to understand, I think by generally understanding these limit types of concepts that involves both first principles, limits, continuities, and everything, I think this is going to broaden your understanding more about the calculus. And now, from our next lecture, we will be going on more further into differential calculus, perhaps, if possible, I think the derivative functions. Yeah, let's try to cover as much as we can on the next lecture. Thank you for listening to today's lecture, and see you next time. Thank you.